Alright, hi everybody. So let's finish up chapter 12 today. So in 12.5 we're looking at predictions, so a pretty short section, but just on the idea of using our linear regression, so our line of best fit, to make predictions about values that we don't know. So here in our first example, so we have data are collected on the relationship between the number of hours per week practicing a musical instrument and scores on a math test. The line of best fit is y hat equals 72.5 plus 2.8x. What would you predict the score on a math test would be for a student who practices a musical instrument for 5 hours a week? So in this case, we're looking at the relationship between number of hours per week practicing and scores on a math test. So when we're looking at 5 hours per week, that's going to be our input variable x in this case. So for the appropriate score, we would be looking at 72.5 plus 2.8 times 5 hours per week spent practicing. Add those values up, that gives us 86.5. So what we would say is we would predict a score of 86.5. Okay. Now, this prediction can be helpful, particularly when we don't have data points at that specific value. So maybe we have people who practice, 3 hours a week, 4 hours a week, 5.5 hours a week, but maybe not 5 hours exactly. We could use this to get a good estimate based on the data of what the score might be around that number. So we can use this for any number as long as it's within the scope of our data. So this is where we've talked about this a little bit in the last one, but we want to just touch on the difference between interpolation and extrapolation. So interpolation is the process of predicting inside of the observed values within the data. So keyword inside. And extrapolation is the process of predicting outside of the observed values within the data. So when we're looking at predicting, so if we have our data points all in here, our linear, our line of regression here. So if I'm looking at data points within this range here, I can interpolate. Okay, and I can say, well, what would I predict the value to be at this value right here? And I say, well, based on the line, it would be right about there. Okay, whatever that value is. That would be interpolation, and that's what we would like to do with these lines of best fit. Extrapolation is when we start looking beyond. So we look beyond the scope of that data set, and I start using this line to make predictions outside of there. And I say, well, what about at this value over here? And we say, well, it's probably going to be about that. This is the type of predictions we do not want to make. So, and that we mentioned last time, going beyond the scope of the model is never a good idea because you don't know what the data points do after you kind of cross this threshold, right? The data points could all of a sudden just start dropping down here, and we don't know that. So, best to not make predictions using extrapolation, only interpolation. Okay, so only working within the model, not outside of the model. Okay. And then we have an example of why we don't do that. So find the predicted score on a math test for a student that practices a musical instrument 150 hours per week. Is this interpolation or extrapolation, and why? So here we have our formula. So y hat, that's 72.5 plus 2.8 times 150, and that's going to be, if you add those up, 492.5. Now, hopefully, when you're looking at this, you can see just how ridiculous this is for so many reasons. So this is extrapolation. Okay, so this is extrapolation because we're certainly working outside of the scope of the model, right? So this is beyond the scope of the model. Okay, and I can tell you because the result of this, the interpretation of what this is telling us, is that we would expect a score of 492.5, and that's problematic, right? So a couple of things that are just really really impractical about this. So first of all, 150 hours per week practicing their musical instrument. I don't even think any professional musician in the world is practicing 150 hours per week because there's only 160 some odd hours in the week total, and they have to sleep. So that's not practical. And then getting a score of 492.5 is certainly not practical on an exam, presumably out of 100. Like 100% or something like that. So this is extrapolation, and this is the danger of extrapolation. Of course, in this example, we know that this is ridiculous, right? This is way beyond what we would consider normal. But if you extrapolate in a more reasonable range, it might not look so bad, right? If I were to say, well, maybe not 150, but maybe drop that number down a bit lower, but it's still beyond the scope of our model, the numbers might look more reasonable and you're tempted to use that data, but if you're extrapolating, it's still not going to be valid data for the model that we're using. So we got to be careful against extrapolation. So, all right, so that's 12.5. So like I said, a nice short one. So now for 12.6, we're talking about outliers. So in this one, I am going to be using Desmos almost exclusively for this section. So you might want to have Desmos open if you want to kind of work along with me here. If you happen to save any of the graphs from last time, you can work on those, but I'll be showing everything on the screen here. So talking about outliers. So outliers are observed data points that are far from the least squares line. They have large errors where the error or residual is the vertical distance from the regression line to the observed point. So an outlier, so we kind of have a mental image of what an outlier looks like, but if we have a bunch of data points in here, and then our linear regression, and then I have a point that's way down here, right? Something way out of the way. That would be considered an outlier. So we can look at outliers mathematically, we can look at them graphically. So just as a note here, as a rule of thumb, we can flag any point that is located further than 2 standard deviations above or below the best fit line as an outlier. And that's generally kind of how we work with outliers. More than 2 standard deviations away is considered significantly far away. So performing residual analysis on a regression model. So we're going to look at this today. We saw last time in the graphs that Desmos does plot the residuals, those errors. We're going to look more at those today. So residuals play an important role in determining how good our linear model is. In fact, residuals can be used for the following purposes. So to determine whether a linear model is appropriate, to determine whether the variance of the residuals is constant, and to check for outliers. So if a plot of the residuals against the predictor variable shows a discernible pattern, such as a curve, then the response and predictor variable may not be linearly related. Okay, so this is one thing we're going to use residuals for, is to check and see if a linear relationship is actually the best way to describe these two variables. And there could be because maybe there's no relationship, or it could be maybe there's a better way of describing it using like a curve or using something that's not linear. And that's what we're going to be using residuals for. Okay, so let's look at this example. So a chemist has a 1,000-gram sample of a radioactive material, and this chemist records the amount of radioactive material remaining in the sample every day for a week and obtains the following data. So we have our days 0 through 7, and then the weight in grams, so it's decaying, so it starts off at 1,000, and then it eventually works its way down to 468.3, and he's recording it every day. Okay, so we're going to be looking at the scatter plot with the least square regression line, find the linear correlation coefficient, so that's R, and use a residuals plot to determine whether the linear model is appropriate, and use 3 decimal places when rounding if need be. So I went ahead and plotted this on Desmos in a table, so let me pull that up for you right now. Okay, so here we have our data. So we've got up here 0, 1000, 1, 897.1, etc., all the way down to that last value. And then Desmos, of course, plots the residuals here in their own column. So Desmos has this all ready to go for us. So, and I went ahead and made the linear regression down here. So we can tell already the R value is right here. So that's going to be negative 0.9941, and if it says round to 3 decimal places, so just 0.994, right? Negative 0.994. So that is a very strong correlation, right? That's almost negative 1, and negative 1 would mean that there's almost a definite correlation between the two variables. Okay, so that one's going to be our R value. Now let me go ahead and show you this data. Now obviously we can't see it right now. That's because look at where these values are. This is 1,000, 700, 400. The lowest value is 468. So we need to change our scale a little bit. So my y-axis, all these values go, the x's go from 0 to 7. So I'm just going to go just outside of that. So, whoops, sorry, that's my x-axis. Negative 1 to 8. Just go just outside those x values. Then the y values go as low as 468, so let's start at 450. And they go as high as 1,000, so let's go up to 1,050. And there's our data. Okay, so those are all our data points. And if I draw that linear regression, you can see where the line is going right through those data points. Okay, so you can see it looks like a pretty good fit, right, for that data set. All right. So now, we got the correlation coefficient, so we got R equals negative 0.994. And then we need to now look at the residuals to see if there is any discernible pattern in the residuals. Because again, if we just recall what we said up here, if there looks like there's a pattern to the residuals, like a curve, then that means that these should not be linearly related. But if there is no pattern, then we say that the line is the best way to go. So let's look at these residuals. So this one, the highest one, like that's 30. They also go down to like negative 23, right, 26. So let me adjust our scale one more time. So y-axis will go as low as negative 30, and we'll go as high as just 35, like that. Okay, so those are our residuals. Those are our errors, okay, for each of these. Now if you look at this, it looks like there's a pattern to me, right? If you start on the upper left one and then go down, it looks parabolic, right? Just kind of imagine filling in those lines there, connecting the dots. It looks like it's got a curve to it, okay? Which means that the linear model is not the most appropriate model for this situation. Now, interesting, you think that might be a little confusing because the correlation coefficient is almost negative 1, right? In fact, that would round to negative 1, right, if we rounded. So why is there such a strong correlation, but this data suggests in the residuals that it's not linear? Well, just because the linear regression line actually seems to fit the data well does not mean that it's the best fit for the data. And what this suggests, if you go back and look at the data, if I go back up to 400 and 1100, go back and look at this data, it does look linear, but if you notice, maybe if I zoom in just a tad bit more, 150 and 450, like that. Notice there's a bit of curve to it. It's very slight, but here's the line. You can see a little better that way. Notice that it has a kind of a bend or a curve. So all this is saying is, even though the line might be a good fit, the line might not be the most appropriate for this situation. There might be another type of regression or a type of curve that is more appropriate to match this data. So that's what we're talking about with the residuals. Not that the line is bad, but that there might be something better. Okay, so let's just summarize that here. So there appears to be a curve pattern to the residuals indicating a linear model may not be appropriate here. Okay. All right. So, and then they offer up another note here. If we're looking at the residuals against the explanatory variable, if that shows the residuals either strictly increasing or strictly decreasing, so only going up or only going down, as the explanatory variable increases, then a strict requirement of the linear model is violated. So if we have that they're either all going up or all going down, then that's a problem. That means that that's definitely not the model we should be using in that case. So not only is it not a curve, it looks like another straight line almost, right? It's all only going up, only going down. That would not be good. So okay, so let's look at this next example. Again, we're going to refer to that drilling time data that we've been working with for the last few sections. So draw a residual plot of the drilling time data, comment on the appropriateness of the linear least squares regression model, and produce a box plot of residuals. So let's go back to that graph. So let me pull it up here. Where is it? There it is. Okay, so remember this is the graph that we were working with before. And I mentioned the residuals, that's these points down here, but we didn't really go too in depth on them. So here's the residuals, and if we look at these, the question is there a discernible pattern or curve that can be applied to these? And just by looking at it, it does not appear so. Right, I don't see any kind of one smooth curve that can hit all those points. They're kind of going back and forth, right, up and down all the time. It doesn't look like there's any sort of discernible pattern here. So I'm going to go with this has no pattern to the residuals. So what that means when there's no pattern is that the linear model is appropriate. That means with the linear model we did a good job picking the linear model to use. Okay, so there is no discernible curve pattern to the residuals. So a linear model is appropriate. Okay, so it turns out that we were doing the right thing using our linear model before. Okay. And then we have identifying influential observations. So an influential observation is an observation that significantly affects the least squares regression line slope and or y-intercept, or the value of the correlation coefficient. So influential observations typically exist when the point is an outlier relative to the values of the explanatory variable, right? Because if I have, all of my data points here, and that gives me that linear regression line, and then I add a data point like way down here, well, in order to take that point into account, the line is going to have to balance it out. So the line might drop to something like that. Okay? And then all of a sudden the y-intercept has changed, the slope of the line has changed, and the correlation is no longer as strong anymore to the data set, all because of one, essentially an outlier. Okay? So we need to take into account if we have any influential observations. So suppose an additional data point is added to the drilling data. At a depth of 300 feet, it took 12.49 minutes to drill 5 feet. Is this point influential? So let's go back and look at the data. Okay, so let's focus on the actual data points up here. Okay, so take note. So let me move this up here so we can see it a little better. So currently, the slope, so the M1 value, that is 0.011553, so about 0.011, right, or 0.012. The y-intercept is about 5.5, and the correlation coefficient is about 0.77. Okay, so what happens when we add in this new data point? So it said at 300, okay, it had a drilling time of 12.49 minutes. Okay, so we added our new data point in, and let's look and see what happened with our data. So in this case, we got a 0.02 slope, so it almost doubled the slope. 0.44 y-intercept, so it reduced the y-intercept by about 1 unit. And then the correlation coefficient actually went up to about 0.86, 0.87, somewhere in that range. So did this have an effect, right? And then again, I can just delete this. And we can see, right, it looks like, right, it's tilting the line up slightly, and it's shifting it a little bit, and it is affecting our correlation coefficient. So, is this point influential? I would say yes, it is, because again, it has an effect on the slope, on the y-intercept, and on the correlation coefficient. I guess it would be up to your interpretation, how you want to describe that. So on this one, as we've seen with lots of examples that we've done in the course, like you can make an argument either way, right? If you said, well, yes, it doubled the slope, but the slope was so shallow that it's still very shallow. You could say, the y-intercept went down by 1. You could say it actually improved the correlation. So it depends on your argument, right? Your perspective here. So, we could say, so slope doubled, y-intercept down by about 1 unit, and R increased by about 0.1. Okay, so is this point influential? Again, you can make an argument either way on that. So I would say ultimately, due to the change on slope and the y-intercept, I would say it is likely influential. But you could make an argument against it. Using the correlation coefficient. Okay. So, and then just a couple notes down here. So as with outliers, influential observations should be removed only if there is justification to do so. So when an influential observation occurs in a data set and its removal is not warranted, there are two courses of action. So you either collect more data so that additional points near the influential observation are obtained, or use techniques that reduce the influence of the influential observation, such as a transformation or different method of estimation. Okay, so the most preferred is usually that one, collect more data, right? So if I've got a value that's outside of my scope and it's pulling my slope down, or it's changing my correlation coefficient, maybe you just go find more data that maybe fills in that gap a little bit, that helps it make a little more sense. So so that's it for chapter 12. So that's the idea of linear regression, of correlation versus causation, right? Influential observations, outliers. And we didn't talk about the box plot, but I can pull out the box plot just really quickly here. So I went ahead and plotted the box plot of the residuals down here, and you can see our residuals are all fairly grouped together. That's just the box plot function of E1, which E1 is just our residuals there. So just showing how they're all grouped pretty tightly, not really any outliers there on the residuals, so that's good to see. So anyways, again, that's it for chapter 12. So that's kind of our discussion on linear regression. This is a very important topic, especially when working with sample data that you want to be able to analyze and determine if you have a relationship between two variables. So we want to see visually, is there a relationship, and also, of course, mathematically, does that support the idea that there is a relationship. So that's it for this chapter and for today's lecture. And so I will talk with you all next time, and we'll